Hello students, so today we'll be discussing Maxwell's equation, which is actually module 3. So Maxwell's equation is not something new equation, it is just 4 equation that is already there in electricity and magnetism, and he actually established the connection between them. Okay, so let us first write the equation and then we'll come to the details of the equation. The first equation that we can write is, that is, it is basically, the first equation is divergence of E, which is equal to rho by epsilon 0, okay, which is we already know, which is Gauss's law, and probably you have came across this Gauss's law in your previous classes. We'll come to the details of it. And so this is divergence of E. The second equation is divergence of B, which is divergence of B equal to 0, which is again we call Gauss's law, but this is Gauss's law in Gauss's law for magnetism. So this is Gauss's law for magnetism. The third equation is actually curl of E, which is minus del B del T. This is known as Faraday's law of induction. Again, probably you know what is Faraday's law, okay? And the last equation, which is obviously the last equation, is curl of B, curl of B is nothing but mu naught J plus mu 0 epsilon 0 del E del T, or there is another form we can write it, which is curl of H, which is nothing but J plus del D del T, where D is the displacement vector, and this is known as modified Ampere's law. Okay, so these are the 4 basic equations. Now we will discuss how we can get this equation from our basic understanding of our previous classes. Okay, that is from the idea of what we already have. The problem with the problem in in this class is that we don't have electricity and magnetism in our syllabus. So I'll be taking into account that you know already some idea about electricity and magnetism. So we have to again go back to our class 11, 12 topics to discuss that. So let us first discuss the Gauss's law in electrostatics. Okay, so if you remember, the Gauss's law states that electric flux through any bounded surface is equal to the charge enclosed within that system. So in mathematical expression, we can write it as E dot ds. E dot ds is electric field dot ds, means it is a surface integral which actually gives the electric flux, the measurement of electric flux. So this electric flux is equal to Q, total charge enclosed, that is Q divided by epsilon 0. If we write it in terms of charge density, then we can write it as rho dV divided by epsilon 0. Now, at the very first chapter in our class, we have discussed Gauss's law in divergence, Gauss's theorem for divergence, and Stokes theorem in vector, and we will be using this a lot in this chapter, and this is why we need to know the divergence theorem. So using that, I can write divergence of E that is divergence of E dv. Now divergence of E is a scalar quantity, so it is a vector dv. You can go back to your first class notes and you can check that. So this is nothing but rho by epsilon 0 dv. Okay, so from here equating we can write that divergence of E is nothing but rho by epsilon 0. So this is the first equation that we have got. Let us consider the second equation, which is Faraday's law. Let us do the divergence of B will not, I'll come to it after this. Let us start with the Faraday's law. Now Faraday's law states that it is the induced EMF is change in flux. So it is E equal to minus d phi dt. And the induced EMF, again we can write it as E dot dl over a closed surface is equal to minus d phi dt, where phi is the magnetic flux. Now similar to the electric flux that we have written in the previous cases, we can write this as B dot ds. So we can write it as integration over closed E dot dl is equal to minus del B del T dot ds. So now we can use Stokes theorem in vector, and I can write it as curl of E dot ds is equal to minus del B del T dot ds. So I can write the last, I can compare it and I can write curl of E equal to minus del B del T. So this is the third equation, that is actually what we have done. Now the point is that we can write this as my equation 2. Okay, I can write this as my equation 1, and if I take the divergence of 2, okay, so taking divergence of equation 2, we can write divergence of curl of E is equal to minus del del T of divergence of B. Now divergence of curl of anything is 0. So this is 0 always. So this gives me that divergence of B is equal to 0, which is equation 3, and which we can call it as Gauss's law in magnetism. Now the last one, that is the Ampere's law. Okay, the last one is known as the last Maxwell's equation is known as the Ampere's law, which is actually not the proper form of Ampere's law. This is the modified Ampere's law. So we have to be very sure about the last one, because this is the most important question of this chapter. Okay, so let us first start with Ampere's law. Okay, now we know that Ampere's law states that B dot dl is equal to mu naught I. If you remember that, so I can write it as mu naught I as mu naught. In terms of current density, I can write it as J dot ds, where J is the current density. So I can take the, again I can apply Stokes theorem, and I can write it here that curl of B dot ds, it is a surface integral, is equal to mu naught is a constant. I can take it inside the bracket, mu naught J dot ds. So this is curl B is equal to mu naught J. Now if you compare this, you can check that when we have written the Maxwell's equation for the formula, so curl B equal to mu naught J only gives me the first portion of it. There is some other term here which we need to know how it is come. So actually the problem is that if we can apply Ampere's law in some cases, it is not some universal thing. So Maxwell modified the Ampere's law, and that modification actually, so contribution of Maxwell in this whole set of equation is this modification, and he actually established the connection that all the equation are connected. Okay, so let us try to find out the modification. Okay, so modified Ampere's law, or I can say the Maxwell's contribution, Maxwell correction. Okay, so as we know from Maxwell Ampere's law, we have curl B is equal to mu naught J. This is our equation 1. If we take divergence of that, so taking divergence, I can write divergence of curl of B, which is mu naught divergence of J. Now divergence of curl is always 0, so 0 is equal to mu 0 divergence of J, which actually gives me that divergence of J equal to 0. Let us write it equation 2 here. Now the problem is, if you remember that there is a something called continuity equation in our electrostatics or electricity chapter. From continuity equation, what we can write is actually divergence of J is nothing but minus del rho del T. So this actually contradict each other. So from one case I can say divergence of J is equal to 0, in other case divergence of J is del rho del T. So the problem is that it is only true if del rho is constant. Now to make it universal, that it is only so basically this is only varied for static charge density. So static charge density means where it is electrostatic, so charge density is constant, so my rho is constant, del rho del T will give me 0, and this will be hold simultaneously. But for time varying field, which is the current electricity, okay, so there rho is not a constant, rho is changing. So time varying field, it is not correct and it needs to be modified. Okay, so actually the problem is that what we put it curl B equal to mu naught J, it is not only J, there should be another term added to that. Okay, so for correction, what Maxwell did, he said actually this curl of B is not only mu naught J, but there is some other term, let us call it M. Okay, now if we take the divergence of this curl of B, okay, so we have mu naught divergence of J plus divergence of M. So this side is 0, so that means mu naught J plus divergence of J plus divergence of M is equal to 0. Okay, so we can write divergence of J is equal to minus divergence of M, that is equal, so divergence of M is minus divergence of J, that is equal to del rho del T. Okay, okay, so this is one of the form of M we have got. Now from Gauss's law, we can say that divergence of E is nothing but rho by epsilon 0. Okay, So therefore we want to find out one form of this del rho del t. So this rho is nothing but epsilon 0 divergence of E. Okay, so divergence of M, we can write it del rho del t, that is equal to epsilon 0 del t of divergence of E, which is nothing but epsilon 0 divergence of del E del t. So this is divergence of del t of epsilon 0 E, because epsilon 0 is a constant. Therefore we can write M is nothing but del t of epsilon 0 E, which is del d del t, where d is the displacement vector, and we will be discussing this displacement vector in our dielectrics chapter. Okay, so now we can write the modification. After the modification, that curl of B is equal to mu 0 J plus M, which is mu 0 J plus epsilon 0 del E del T. So we can write it mu 0 J plus J D, where this is called displacement current density. Okay, so this is the 4 equation, and the modification is very important. Okay, and we can also write the integral form of this. Okay, so let us also write the integral from. Generally the question comes like, write down the Maxwell's equation. So if the Maxwell's equation you have to write, you can write the divergence of E, divergence of B, curl of E and curl of B. Integral form hardly comes, but sometimes it can be asked that write down the integral form. So we have to write like this: integration E dot ds equal to q by epsilon 0. This is first one. The second one is, we can find out actually divergence of B is 0. So from here I can write divergence of B dv equal to 0. So this means we can write B dot ds equal to 0. The third one is curl of E is equal to minus del B del T. So this is, I can write as curl of E dot ds. Stokes law. Actually we have done this in the reverse way. We have done it. So del B del T dot ds. So we can write it as finally that E dot dl is equal to minus del t of B dot ds. This is the third one. And the fourth one we have done right now, so I am not going to do the detail. It is, we can similarly, you can show that B dot dl is also mu naught IC plus ID, where IC is the conduction current and ID is the displacement current. Okay, so these are the 4 equations we are having. Now what is the physical significance of each of the equation? So I'm not going to write it here in the video. So I have already sent you one class note. So please check there what is the physical significance. Let us go to the first page and let me discuss what is the physical significance. Okay. So the Maxwell first equation signifies the total electric displacement through the surface. So it gives you the total electric flux passing through any surface, which is essentially the Gauss's law. So when you are writing the physical significance, you have to write it. You can mention the name of the law also for your understanding, for the examiner's understanding. That is not a problem. Okay. The second one is very, very important. The divergence of B is equal to 0. Now, what does this mean? Divergence of anything means, if you know that divergence of anything, if it is positive, okay, that means there is a source. If it is negative, then there is a sink. Okay. So if I have divergence of B, if it is positive, then I have a source. If I have divergence of B negative, then I have a sink. Okay. Let us take one example, simple example. I have a positive charge here. Okay. So the electric field lines will be moving out of this. Okay. Now I can consider a surface. Let us say this red one is my surface, and I am measuring the divergence here. If I take negative charge at the center, then electric field lines will come into that surface. Okay. So this is like this. So here divergence is positive, here divergence is negative. Clear? Now if I have this kind of charges where I have both a positive charge and a negative charge and I have a surface, then what happens is that electric field lines will generate from this end at this. Okay. So it will come here, but again it will come back here. So one going out, one going in. So divergence is 0. Now for electric field, I can have one positive charge, I can have one negative charge individually. So I can have divergence positive, I can have divergence negative. But for magnetic field, it is always, these two cases does not exist. So it is always divergence of B is 0. So divergence of B0 means it is always the case is like this. So I can say that magnetic monopole cannot exist. That means you cannot have a single north pole or a single south pole. You always have to have, if you break one north and south pole, so it is always, if you have a this, it is always north and south, and if you break it, the new one, you will be getting north and south and another north and south. You will not get a single north pole or a single south pole. You cannot get it. So magnetic monopole cannot exist. This is the second physical significance of the second law. The third and fourth law is again more essential for electromagnetic wave purpose, and it's actually proved that changing magnetic field can produce electric field, and also changing electric field can produce magnetic field. So what Faraday's law says? Faraday's law says that if the magnetic flux changes, then induced EMF generates. So that means if you have a changing magnetic field, you can have a electricity. Okay, this is given by this law. So Maxwell's third equation signifies that the electromotive force, which is called the EMF, around a closed path is equal to the negative of the rate of change of the magnetic flux around that. Clear? So this is changing magnetic field gives you electric field. Now the fourth law gives, Maxwell fourth law says that magnetomotive force, just like electromotive force EMF, this is magnetomotive force. This can be generated by changing electric field here. Okay, so this is the changing electric field. So the Maxwell fourth equation signifies that the magnetomotive force around a closed path is equal to the conduction current, which is this. And again, you can go back to what we have written, that this is conduction current plus the displacement current bounded by the path. This is the physical significance. You can check the class notes. Okay. Now the wave equation for free space. So it is not clearly mentioned in our syllabus whether the wave equation is there or not. It is only written Maxwell's equation. But some time back I have seen that it has come into the question in university exam. So let us discuss that, the Maxwell's what do you mean by wave equation and how it is coming. It's already there in our class note and also the PDF or slides that I have shared with you. So you can check there the time varying electric field in free space. That is the so you can go back and check there. Okay. So what happens is that let us do it for the electric field first. Okay. So okay. So let we know it is for electric field. So we'll start with curl of E. We know curl of E is minus del B del T. Okay. We can take the curl in both side. So taking curl on both side gives me curl of E, which is minus del T of curl of B. Now curl of E is an identity, that is you can go back to your first chapter, okay, in the vector, and there are something like 12 identities I have written. So we can use one of those identities for curl of E, which is written like this: gradient of divergence of E. Remember that this is gradient, so I have not put a dot because this is a scalar, minus grad square E. Now this grad square E is an operator called the Laplacian operator. Okay. Again we have used this in our class, is equal to minus del T of curl of B. Now this curl of B, I know this curl of B, this gradient, this divergence of E, this is actually 0, the first one. Okay. So we can put it like this. Say this first one will be, let us say divergence of rho by epsilon 0 minus grad square E, that is equal to minus del T of, now this curl B equal to the equation is J plus del D del T. Go back to your class notes, open your class notes while checking the video. That will be better for you. Okay. Now, in free space, what happens is that this is the form that I have written in general case. In free space, I have divergence of E equal to 0 because there is no electric field, there is no charge present. The divergence of B is 0 everywhere. This curl of E is minus del B del T again. And this curl of B, it is important. The curl of B is also, it is only the mu naught epsilon naught del E del T, because in free space there is no charge. So if there is no, okay, so we are discussing time varying electric field. So this is what we got. So in free space we have these equations. So from the previous equation where we left, we can actually write grad square E equal to mu 0 epsilon 0 del E del T. So we can write that mu 0 epsilon 0 del E del T. Okay. Similarly, taking curl on equation 4, that is the last Maxwell's equation, we can write this as curl of B we can write curl of B, which is nothing but mu 0 epsilon 0 del t of curl of E. So again we can write it as gradient of divergence of B minus grad square B. This is equal to mu 0 epsilon 0 del t of minus del B del t. So we can write it as grad square B equal to mu 0 epsilon 0 del 2B del T2. Now we have this is the field equation, we can call it, this is the field equation of electric field, this is the field equation for magnetic field, because the general field equation looks like this: grad square psi is equal to 1 by c square del 2 psi del T2. So therefore we can write it as that c equal to nothing but root over mu 0 epsilon 0, and it is 2.9998 into 10 to the power 8 meter per second, which is the velocity of light. And also, though we don't have the detailed calculation, but I can show you that E0 by B0 is nothing but omega by k, that is equal to c, and k cross E is equal to omega into B. So from here we can say that electric field is much more than the magnetic field, and this is the reason that we have choose electric field as our optical vector in our case of polarization. And from here we can also say that k cross E equal to B, so that means both electric field, magnetic field are perpendicular to each other, and they are perpendicular to the direction of propagation vector. Okay, so this is actually what we all have from this Maxwell's equation. So we'll be coming back with the dielectric in the next class. Okay, thank you.